So in this video I'm going to talk a bit about superposition and then how that relates to stationary waves, because you need superposition to create stationary waves. So it makes sense to address superposition first. So what is superposition? Well, that's when two waves meet and their total displacement, so the displacement of the resultant wave, is equal to the sum of the two individual displacements. That raises the question, what is displacement? So you haven't covered this yet, maybe you got to this chapter in Unit 2. Displacement is the vector equivalent of distance, so it has magnitude just like distance does, but it also has direction, so it can be positive or negative. Next thing you need to know is what a coherent source of waves is. So it's a source that produces waves of constant phase difference. So the phase difference between two sets of waves is fixed, it's not changing, and that's something that's going to be important. And then there's monochromatic, which is when a source produces waves of constant wavelength and frequency. So for instance, lasers are monochromatic, and they're very highly monochromatic, so they give you a very accurate constant wavelength of light, which is very useful, as you'll see later on when we start to look at some of the slit experiments. Okay, moving on. So the thing you need to know about is constructive and destructive superposition, or sometimes constructive or destructive interference. So we have these two waveforms you can see here at the top. So if we look at the two waves here, you'll see they're at the same points at the different slots in time, at least for the first full cycle. So these waves are in phase, or they're 0 degrees out of phase with each other. So what superposition tells you is that the resultant will have the sum of the displacements on this. So if we're drawing the resultant, what you'd expect to see is the amplitude of the sum of these, and then it would be like this. Because if we can see here, at this point here, we've just got one wave going, so that's why you get the smaller peak there, and this peak here, so is equal to, so if we call that A, then we call that B, and we call that C, so it should be A plus B, so it's the sum of the two amplitudes there, and you get the same thing here. If we call this one here D, you'll see this one would be D as well. If we look at destructive, in this case they're 180 degrees or pi radians out of phase. See, as this one goes up to a maximum, this one goes down to a minimum. So what you get here, because displacement has direction, when you add them together, they'll end up cancelling each other out. So if we switch the waveform, again, like this, but then noticing we've got the peak down here where we have only a peak on this one, but not on this one. So when this peak here is equal to this one, you get this flat section because they completely cancel each other out. And those are the two types of superposition you need to know about. And most commonly, this is the kind of superposition you'll come across, either completely in phase or completely 180 degrees out of phase with each other. Otherwise, it gets very complicated sketching these. Okay, so an example of this would be sound wave interference. So if you get two speakers and you face them both the same direction, playing the same sound, so you need to make sure your speakers are on the mono setting, because if you put them on the dual, it will split different sounds between them, but you want them producing the same sound. So if they're on the mono setting and they're producing the same sound out of these wavefronts here show the passage of the sound waves through space. And the key thing in all of these is the path difference. So if we can draw this line here, this is exactly halfway, I mean, not in this diagram, but it should be exactly halfway between the two speakers. So the waves will have travelled an equal distance to get to these points along this line. So the path difference between the waves is 0. So if you're walking along, you've got 0 path difference And so when you get there, you will find it is very loud because you've got the two waves superimposed on top of each other, so it's extra loud. So let's add in a few more points. Okay. So at these points I've marked in here, you've got the path difference as a multiple of the wavelength. So we've got these ones here where the path difference is the wavelength over 2, and we've got these ones where the path difference is a whole wavelength. So first of all, we need to know how to convert from path difference to phase difference. So the key equation you're going to need to know is that the phase difference is equal to this, where this here is the path difference. Okay? So we put this lambda over 2 into this equation, you get 2 pi lambda over 2 lambda, which equals pi. So at that point, the waves are 180 degrees or pi out of phase, so you get complete destructive interference, so you get nothing. In reality, that's not what's going to happen. It's just going to go a lot quieter, but that's what you're going to find. So if we go up to lambda and put that into the equation, you'd end up with 2 pi lambda over lambda, so you get 2 pi, and that's the same as being 360 degrees or 0 degrees out of phase, so you get it being loud. So, and it's the same down here. You would get nothing at this point and it being loud here. And this is the key equation at play here. So how you convert the path difference d into phase difference, which would be what the result of this overall calculation here. And I urge you to try this out. This is a really cool thing you can try and hear working if you set this up properly. So we're going to take a look at stationary waves, and as I said earlier, these are created by superposition, which is why I looked at that first. So they're created by superposition of progressive waves, but they're travelling in opposite directions. So if you have microwaves reflected off a surface and coming back, they'll be superimposed on top of the microwaves going towards the object they reflected off, and you get a standing wave set up. And the key thing is, no energy is transmitted by a standing wave because it isn't going anywhere. So all that's happening here is that the particles are going up and down like this. They're going up and down like this. They're not going all the way along. So each of these points here is just moving up and down. So they're moving perpendicular to the motion, what it looks like as you move along here. And the key thing is the amplitude changed on the waveform. So this here isn't the only amplitude. This is an amplitude. This is an amplitude. This is an amplitude. This is an amplitude. So there's different amplitudes along the way. A couple of key things to identify. This here, where your amplitude is 0, is called a node, and where the amplitude is at a maximum, it's called an antinode, like this. And though that notation becomes useful as we go through some examples of this. So, harmonics. So here, where you can see half the waveform here, so they're giving you the half the wavelength between 2 points. If you see a wave like this, it's called the fundamental harmonic. Okay? And the next thing is, well, what about the other harmonics? Any of you who are musically minded will have heard of harmonics. So there's something called the second harmonic, which is exactly half of this one. So goes like this, and this is called the second harmonic, which is sometimes known as the first overtone. And then, following on from that, there is a third harmonic, and let's try and get this right. So that should go like this, so you get 1.5 wavelengths in the same distance, and this is your third harmonic. per second overtone. The other key thing to draw your attention to here, so this fundamental wave here, this would be called the natural or frequency or the resonant frequency of the string or whatever you're producing this wave in. And that's quite significant at A2 where you start to look at simple harmonic motion and that sort of thing. So it's a useful flag here. So this one, the fundamental one, would be at the resonant frequency of the whatever system you set up this wave in. And like I say, that's more important at A2, but it's something you might want to take a look into. So one of the key things you need to do, and I wouldn't be at all surprised if this was the content of a longer answer type question, is the difference between stationary and progressive waves. So the key thing is that for progressive waves, all particles vibrate at the same frequency. There are no exceptions to that. But in a stationary wave, at the nodes, so at these points where it's 0, these aren't actually vibrating with any amplitude at all. So equivalent, they're not vibrating. So then they're not going to be vibrating at the same frequency that the rest of them are. But the rest of them will be at the same frequency, but just not at the nodes because those are at 0. On a stationary wave, you've got these different amplitudes, so the amplitude changes as you move along the wave. Whereas on a progressive wave, this here is the amplitude, so stuff goes up to a peak, down to a minimum, up to a peak, so it's travelling along this way. So this here is the amplitude, and it's the same for all the particles the wave travels through. So in terms of the phase difference between two particles, we've got it being m pi, so where m is the number of nodes between particles. So it's the number of nodes. Number of nodes between the points. So if we look at this diagram down here, A and C. So they've got 2 nodes between them, so their phase difference is 2 pi, so that's 0, so these are in phase with each other. Look at C and D. There are no nodes between these 2 points, which means they are 0 pi out of phase, which means again these 2 points here are in phase with each other. Look at A and B. There is 1 node in between here, which means they are 180 degrees or pi radians out of phase, so they are at complete opposite sides, which you can sort of see from this diagram here. Not quite the same here with the progressive wave. So we've seen this here equation here earlier. If you look at this diagram here, A and B, so we've got half a wavelength between A and B. Put that into your equation, you get pi, so you've got 180 degrees or pi radians out of phase, so they're completely out of phase with each other. Look at C and D. We have gone a quarter of the wavelength, so lambda over 4. We put that into our equation, we get pi over 2, so then 90 degrees or pi over 2 radians out of phase with each other.